Okay, this is chapter 6.3, Logarithms and Logarithmic Functions. Essential question is, what are some of the characteristics of the graph of a logarithmic function? Every exponential function of the form f of x equals b to the power of x, where b is a positive real number other than 1, has an inverse function that you can denote by g of x equals the log base b of x. And that's how you read that right there. Log base b of x. This inverse function is called a logarithmic function with base b. Okay, so we'll get into all of those terms and all of that stuff in this chapter section. What you will learn is how to define and evaluate logarithms, use inverse properties of logarithmic and exponential functions, and graph logarithmic functions. So let's take a look. Okay, so first of all, a logarithm. What is a logarithm? You know that 2 squared equals 4, and 2 to the third power, or 2 cubed, equals 8. However, for what value of x does 2 to the power of x equal 6? So 2 to the first power equals 2. 2 squared equals 4. And 2 to the third equals 2 times 2, which is 4, times 2, which is 8. So notice that 6 is between 4 and 8. So we know that 2 to the x equals 8, that x would have to be, our power would have to be between 2 and 3. So it'd be 2 point something. Okay, and that's what we're going to find using logarithms. Okay, so basically that's what it is. A logarithm is an inverse of an exponential function. So the core concept, definition of logarithm with base b. Let b and y both be positive real numbers with b not equal to 1. Okay, so b has to be positive and not 1. So it's 2, 3, 4, 5, 2.5. Positive real numbers not equal to 1. The logarithm of y with base b is denoted by the log base b of y and is defined as the log base b of y equals x. If and only if b, our base, to the power of what it's equal to, equals what we're taking the log base b of. Okay, this is going to take a little bit of practice, but it's actually not too bad if you understand the foundation of the chapter section and this one in particular. If you can understand this chapter section, logarithms should be much easier for you. Okay, so the expression log base b of y is read as log base b of y, as I've been saying. So this definition, it tells you that the equation log base b of y equals x and b to the power of x equals y. So what I tell my students is go around in a counterclockwise circle, starting at your base, go over to the other side of the equal sign and come back to here. And that's the order of this. B to the x equals y. The first is the logarithmic form, log base b of y equals x. And the second is the exponential form. Okay, and so let's take a look at that in example 1. Okay, so here we go. Example 1, all we're doing in this example is rewriting a logarithmic equation and putting it into what's called exponential form. So you start with your base 2. So you're going to write 2. Always start with the base, go over to the other side of the equal sign, and that's your power, and then continue over back across the equal sign to the number we're taking the log base of. So this is log base 2 of 16 equals 4. That means 2 to the 4th equals 16. Okay, it's very simple. Here's a 4. That's my base. 4 to the power of what's on the other side of the equal sign equals what's back here that we're taking the log of. And 4 to the 0 does in fact equal 1. 2 times 2 is 4, times 2 is 8, times 2 is 16. So that is also true. These should all be true equations. Again, we have the log base 12 of 12 equals 1. So you write the base 12, go over to the other side of the equal sign. That's your power. And what's over here is the number that you would get if you took your base to that power. 12 to the 1 is 12. So log base 12 of itself is always going to equal 1. And log base something of 1, log, no matter what your base is, the log base of whatever to the 1 is always going to be 0. Okay, so now we have a fraction. Okay, no big deal. Fraction. You take 1/4, I'm going to put it in parentheses, to the power of -1 equals, go back around to the other side, 4. So 1/4 to the -1 equals 4. So that is rewriting equations in exponential form, just like that. Okay, so now you should be able to do problem numbers 5 and 6. Okay, so now we're going to rewrite exponential equations. We're going to rewrite each equation in logarithmic form. So this is an exponential form, and we're going to put it into logarithmic form. So 5 squared equals 25 is a true statement. Our base is 5. So the first thing you're going to do is write the word log. And since our base is 5, that's our little number that goes down as like a subscript. So it's the log base 5 of what's on the other side of the equal sign equals your power. So log base 5 of what it's equal to is equal to the power. It's pretty simple once you do a few of them. So what's our base here? It's 10. So we're going to do log base 10 of 0.1 equals -1. Okay. I'm going to say something here that the book didn't mention yet. Log base 10 is assumed, just like the square root of 9. We always assume the index is 2 if there's nothing there. We do the same thing here. If it's log base 10, we can just simply say the log of 0.1 equals -1. If you have a base 10, you don't have to write it. Okay, and now we have a base of 8, so that's log base 8 of what we're equal to, 4, is equal to 2/3. Okay, and then finally, our base is 6. 6. So we're taking the log. Let me rewrite that. I forgot to write the word log. We're taking the word, we take the log base 6 of what it's equal to. So that's 1/216 equals -3. Parentheses aren't necessary, but I like to put them when there's a fraction. You could also write this log base 6 of 1/216 equals -3. Either one's acceptable. And if you want to put the base 10 there, it's probably a good idea to do that just when we're getting comfortable with where things go in the conversions. Okay, so now you should be able to do problem numbers 11 and 12. Okay, so now we're going to do some basic things that show us how these rules work. So it says to evaluate each logarithm in example 3, and it gives us a log base 4 of 64. So what I would like to do is switch that to an exponential function. So you take the base 4, log base 4. Now think of this as equals some value that we don't know. So you say 4, base 4 to the power of what's on the other side equals 64. So what this question is really asking, and when it says what's the log base 4 of 64, it's saying what number in the exponent for 4 would give us 64. So I could say, well, 4 times 4 equals 16, and 16 times 4 equals 64. So that's 3/4. 4 times 4 times 4, or 4 to the third power. Therefore, 4 to the third equals 64. And then, so the log base 4 of 64 is our power. So then I would say the log base 4 of 64 equals 3. Okay, our exponent is what we're trying to find. Okay, so let's try that again. Log base 5 of 0.2 equals some variable x. And so I take the base 5 to the power of x equals 0.2. Okay, well, in order to get a decimal, 5 to the 1 is 5. 5 squared is 25. 5 to the third is 125 just keeps getting bigger and bigger. So I'm thinking if I have to get a decimal, it's getting smaller. X has to be negative. So I'm going to try -1. So 5 to the -1 equals 1 over 5, 1/5. And if I multiply the top and bottom by 2, I get 2 over 10. Ooh, 2 over 10 is 2/10. If you say that, it's 0.2. So there it is. X equals -1. And so we would say the log base 5 of 0.2 equals -1. Okay, so if you're going to get a number that's a decimal from a base that's a real whole number or integer, then the exponent must be negative. Okay, so now let's do C. The log, so I'm going to put it equals X here. So I'm going to take the base, 1/5 is my base, to the power of X, oops, to the power of X equals 125. So we want to try to figure out what 1/5 to the power of. So what I really want to do is, I know it's negative because if I take 1/5 to the first, it's 1/5. If I take 1/5 squared, it's 1/25, and it's getting smaller. So I know my variable or my power is going to be a negative, and that will flip it, remember. So if I think of that as being some 5 to the -1, well, 5 to the -1 is 1/5. And 5 to the -2 is 1/5 times 1/5, which is 1/25. So 5 to the -3 is going to be 1/5 times 1/5 times 1/5. And 1 times 1 times 1 is 1. And 5 times 5 is 25 times 5 is 125. And we got our number there. So 5 to the -3 is 1 over 125. So therefore 1 over 5 to the power of -3 equals 5 cubed, which is 125. So we found our, oops. So we found our power right here. 1/5 to the -3 is 125. So then I'd finally say the log of 1/5, log base 1/5 of 125 is -3. Okay, so be careful with your negatives. You have to remember your exponent rules or you're going to be struggling with this. Okay, so now we have log base 36 of 6 equals some variable. That's how we start it. So we take the base 36 to the power of X equals 6. Okay, again, the number's getting smaller because 36 to the 1 is 36. 36 squared is a really big number, over 1,000. We're getting bigger, bigger, bigger. So we want to get smaller. So therefore the X has to be a negative number. So I would say to myself, well, let's see, 36 to the 1. Actually, this isn't going to be a negative because we're not getting a fraction answer. It's just getting smaller. We want this to be a negative number. So 36 to the -1 is 1 over 36. And don't write this. I'm just thinking 36 to the -2 would be 1 over 36 times 1 over 36. Well, this isn't working. So it's getting too small. So we're missing. And if we do positive, that doesn't work. So how about we do fractions? So 36 to the 1/2. Now, if you remember your rules from chapter 5, if you have a base to a power of a radical, the denominator is your radicand and your numerator is your power. This is the same as the square root of 36, if you don't remember that. And obviously the square root of 36 is 6. So we found it. So that is our X that we were looking for. So I would say the log base 36 of 6 equals 1/2. So there, sometimes you might see a perfect square here. And if you take this number and square it and get that 6 times 6 is 36, or if this was a 7 and that's 49, or if this was a 4 and this was a 16, you're going to get a 1/2. Okay, so now you should be able to do problem number 17 and 18 after seeing these examples. Okay, so now we have what's called a common logarithm, and that is a logarithm with base 10. It is denoted by log base 10 or simply by log. So as I said a couple examples ago, if you have a base 10, you don't have to write it. So you can just say the log of something and you know that that's a common log or base 10. A natural logarithm, okay, is a logarithm with base e. Okay, so maybe you don't remember what base e is, but let me just highlight that right there. The number e. So if I get my graphing calculator out here, and right here over the equal or the division symbol is a blue E. So you hit the second button and the division symbol to get the number E. If you hit enter, it gives you this number, 2.718281828. That is Euler's number. That's why it's called E. Euler spelled, oops, forgot to switch back to pen. Euler spelled E-U-L-E-R was a mathematician, and he has been they named base E after him. So it's Euler's number E. So going back to the calculator, if you look over here, you see e to the x. So if I hit second, that you can take e to a power just like that and find out what that number is, which is 2.718 to the power of 7. Okay, so there's e to a power, and e is over here on the TI calculator. Okay, so it can be denoted by log base e, but is usually denoted by ln. That means natural log, and the ln button on the calculator is here, and the log button is here. So if I take the natural log of 8, for example, that would be like saying the log base e of 8 is that number. Okay, so natural log is where that comes from. It's the natural logarithm base e. So log base e is the natural log ln. Common log is just base 10. All right, so with that said, let's take a look at the next example. Example 4, evaluating common and natural logarithms. So now it's saying evaluate log 8. Remember, that's base 10. So a log 8 is simply, what I can do is put a little 10 right here. And if we want to find the value of it, think of it as that. So you say 10, and I write the x. Woo. So I would say 10 to, oh, let me color code it. So let me switch it to red. Base 10 to the power of x equals 8. Okay, so it says to evaluate this in using your calculator and round your answer to 3 decimal places. So what we're trying to find is the number. So 10 to the 1 equals 10, and 10 to the 2 equals 100. And so I now know that since 10 to the 1 is 10 and 8 is less than 10, I know that x has to be less than 1. Okay, so if you get a feel for this, you can kind of approximate what something might turn out to be. They said to use our calculators to do this. I just want to find the log of 8. So I go to my calculator, clear. Let me minimize this, by the way. There we go. And so the log button is right here. So you hit log, and you hit 8, and you hit enter. And as I said, it's going to be less than 1, and 0.9 is less than 1. So I got the log, so I'll just write log of 8 equals 0.90, and it said round your answer to 3 decimal places, 903. Look at the fourth one, it's less than 5, so we just truncate 9.03. So log base 10, or just simply the common log of 8 is 0.903. All right, Let's try it again. Now we're looking for b, which is the natural log of 0.3. Well, what that means is if I said equals x here, the natural log just means log base e of a number. So that would be e to some number equals 0.3. So try thinking this through and try rearranging this stuff and figuring out what your goal is here. So natural log is base e. E to some number equals 0.3. In the calculator, there's an ln button. And we just put 0.3 in the calculator and we hit enter and we get the natural log of 0.3 equals negative 1.2039. We'll round to 204. Okay, so there is that. And there's one mistake I made. Hopefully you guys caught it while you're writing this. Whenever you're doing an approximation and rounding, it is not an equal sign, it's an approximation. So I need to fix that. So log base 8 is approximately 0.903, and the natural log of 0.3 is approximately negative 1.204. Okay, so this is just simple plugging into your calculator. And so now you should be able to do problem numbers 27 and 28. Okay, now we're going to talk about inverse properties. So by the definition of a logarithm, it follows that the logarithmic function g of x is equal to the log base b of x. And it follows that the logarithmic function g of x equals log base b of x is the inverse of the exponential function f of x equals b to the x. Okay, we already knew that from earlier in this video. This means that g of f of x equals the log base b of b to the x, which equals x. You're probably saying, what? This is putting one function into another function, okay, composed onto. Otherwise known as the composition of functions. Okay, so in other words, exponential functions and logarithmic functions undo each other. So think of 3 and you square it and you get 9. And then you're like, well, I squared it. Now I'm going to take the square root of it and I'm get back to where I started, 3. So if you square something and then take the square root, you're back to where you started. Well, it's the same with logarithms. If you take the log of something and then you take it to that exponent, you get back to where you started. So g composed onto f of x, or g of f of x, equals the log base b of b to the x. And that equals x. And f of g of x is equal to b, the base b, to the power of the log base b of x, and that equals x. So in other words, if you have b log b, they cancel each other out, and what you're taking the base to the log b of x, you just get what's left over. And again here, log base b of b cancels, and you're left with what's left over there, x again. So it is a really simple concept here. So A says simplify 10 to the power of log. Now remember, if there's nothing there, it's base 10. So there is your log. We're over, where is it? We're taking a base of a number right here, b, to the power of log of the same base of a number. 10 to the power of log of the same base of that number. So this 10 to the power of log 10, because if there's no 10 there, it's a common log, you get your power as your answer. So A is simply 4. So now if I take the log base 5 of 25 to the x, well, log base 5, this one's a little bit different. We're going to change this to a 5. It's going to be the log base 5 of 5 squared, which is 25, right? If you will, to the power of x. So the log base 5 of 5 cancels, and you're left with power of powers you multiply. So your power rules really come into play here. So if you do not know what to do with the power of powers rule, you're going to struggle. But the log base 5 of 5, this all basically undoes itself, cancels each other out, undo each other. So log base 5 of 5 goes bye-bye. And you're left with the power of 2 to the power of x. And what powers of powers get multiplied? So you get 2 times x, or simply 2x. Okay, so that is inverse properties. So now you should be able to do problem numbers 35 and 36. Okay, example 6 is finding the inverse functions. It says find the inverse of each function. So we have f of x equals 6 to the x. And I brought in the inverse properties from the last page because it's new, so we can revert back to it without changing the page. So look what we have here. If we have a function g of x equals log base b of x, its inverse is f of x, which is b to the x. Well, notice we have a base to the power of x, and that's f of x. So look at that. That looks just like that. We're just changing b to 6. So if f of x equals 6 to the power of x, then g of x is going to equal the log to the base 6 of x. Not bad, huh? Done. Okay, the next one, y equals the natural log of x plus 3. This one's a little bit different. Hopefully you remember how to find the inverse of an equation. So first you rewrite the equation, y equals the natural log of x plus 3. And when we're finding inverses, we switch x and y. So now it's going to be x equals the natural log of y plus 3. So you switch the x's and the y's, and then you try to get y by itself. So the natural log of y plus 3, well, how do I get rid of the natural log of something? Well, it goes back to this right here, these logs. So if you take the log base b of the same thing, you get x. So if you take the log base e, so let me just say this first before we do this problem. So I'm looking at this right here. So if I had the log base e, and remember log base e is the natural log. So if I took the log base e, or e to the x, make e the base, log base e of something is this. So if I said the log base e of, how do I word this? I'm trying not to, let me see, e to the x. If I had e to the x, then that would be log base e of something, whatever this equals, I'm going to get a value here. So if I don't know what it is, let's call it y. So that'd be y. Log base e of y equals x, then e to the x equals y. Okay, so that's the most general form I could give you without using numbers and decimals that don't stop, that are non-terminating, non-repeating, irrational numbers. So log base e of y equals x, then e to the x equals y. But if I take e to the natural log, well, the natural log, remember the natural log is base e. So what I'm going to do to solve this problem is try to cancel it out. So I want to cancel out the bases. So what I'm going to do here is I'm going to take base e of both sides is what that's called. So I'm going to make e a base of x, and that is going to equal e to the power of the natural log of y plus 3. Okay, so our bases are the same. E to the x equals e to the natural log of y plus 3. So if your bases are the same, your exponents have to be equal, and that's what we had originally. Well, so that will give me e to the x equals Well, e to a natural log of anything cancels, and that just leaves me with y plus 3. So now e to the x equals y plus 3. Remember, all we're trying to do is get y by itself. So now I'm going to subtract 3 from both sides. And I'm going to get e to the power of x minus 3 equals y. So the inverse of y equals the natural log of x plus 3 is y equals e to the x minus 3. So all I'm doing here is just flipping the sides, just putting what's on the right on the left and putting what's on the left on the right, okay? Symmetry. So this is the inverse of this. So now you should be able to do problem numbers 43 and 44, and maybe you should practice these more than just 2 of them until you get a feel for it. But there you have it. Okay, graphing logarithmic functions. You can use the inverse relationship between exponential and logarithmic functions to graph logarithmic functions. We have to look at this concept of graphing before we can do the next example. So parent graphs for logarithmic functions. The graph of f of x equals log base b of x is shown below for b is greater than 1. Okay, so here it is. F of x is log base b of x. It is this red function right here, crossing the x-axis at the point 1, 0. Okay, so that's the log base b of x for b greater than 1. If log base b of x and b is less than 1, but greater than 0, so a fraction between 0 and 1, is graphed right here. So this is what it looks like if b is between 0 and 1. The blue graphs, the g of x's, are the inverse functions of the logarithm or the exponential function. So g of x is b to the x. Because f of x equals log base b of x and g of x equals b to the x are inverse functions, then the graph of f of x equals log base b of x is the reflection of the graph of g of x, which is b to the x, in the line y equals x. So remember that whenever you graph a function like this red one, and you take its inverse, the graph of the inverse will be reflected across y equals x. Same here. Okay, so note that the y-axis is the vertical asymptote of the graph of f of x equals log base b of x. So right here, this is an asymptote. This will never go over to the negative side x. You cannot plug a negative x in. It's not part of the domain. So the domain of f of x of equals log base b of x is all x is greater than 0, and the range is all real numbers. So notice the range is negative and positive. It goes to negative infinity, and this will grow to positive infinity. So the domain is restricted to x's greater than 0. Okay, so let's take a look at graphing these functions. Okay, so here we go with an example on graphing logarithmic functions. So they want us to graph f of x equals the log base 3 of x. Okay, so there's steps to this. Step 1, we want to find the inverse of f. Okay, so let me just slide this thing down, slide it down. To right there. Okay, find the inverse of f. Well, remember, if we write f of x equals the log base 3 of x, first thing you do is switch f of x to y. Okay, and then you remember, let's see, let me highlight this and make it a little smaller. So I want to switch my x and my y. Okay, so all we're going to do is put x where y is and put y where x was. Okay, so I want to get rid of this log base 3. Well, remember the rule, if the base is the same as what you're taking the log base of, they cancel. So I'm now going to take 3 and put it as my base of x on this side and make 3 my base of this right side. So it's log base 3 of y is all the power of this 3. So this component cancels, and we get 3 to the x equals y. So there's our inverse. So I'm going to call it g of x, and that equals 3 to the x. Okay, so there we go. Step 1, you find the inverse. Step 2, let me just erase this now. I went down a little too far. Step 2, you make a table of values for g of x. So here's our table. So we have an x and we have a g of x. So we're going to plug values in. We want to graph around the origin. Okay, and we know that the function is not going to cross the x-axis. Okay, but its inverse will. Okay, so the inverse will cross the x-axis. The original function will not. So the log base 3 of x will not, but if I graph the inverse, then I can reflect. Okay, so I want to graph g of x, and I'm just going to plug values in. So if I put -2 here, so I'm going to do the work off to the side. That means 3 to the -2 equals 1 over 3 squared. Okay, and that's going to equal 1/9. So that's our first value. So I'm going to plot that. I'll use red or blue actually. So if I go over -2, here's 1, here's a half. 1/9 is way down, like right here. Okay, so there's -2 comma 1/9. And then I'll pick -1 as my next value. And so remember, what does that mean? It's 3 to the -1, which equals 1 over 3 to the +1, and you're done. It's 1/3. Okay, so I'm going to plot that point, go back to blue. So -1 up 1/3, which is a little bit higher than 1/9, but it's not quite a half. Half is here, 1 is here. Okay, and then I'm going to choose 0. So I'm going to plug 0 into this, and so that's going to be 3 to the 0 equals 1. Okay, anything to the 0 is 1, so I'm at the point 0 comma 1. So over 0 up 1 is right here. And then I'm going to plug in 1. Okay, so obviously that's going to mean 3 to the first power, which is simply 3. So I get 3 here. And so that's the point 1 comma 3. So go over 1 up 3, which is here. Notice what's happening. It started over here and it's growing and it's getting bigger and it's starting to get bigger quicker. Okay, so now I'm going to pick another value, 2. And that means 3 squared. Okay, so that plug in 2 to our exponent and we get 9. So we get 9 here. So now I'm going to plot that point over 3 or over 2 up 9, which is right here. So this function is going to continue up like so and keep going like that. So it's curving and going up like that. Okay, so now remember, if I graph y equals x, I'm going to reflect across it. So let me get my ruler, and I'm going to graph y equals x, because this is an inverse function. So I want to go up 1 over 1, up 1 over 1. Y equals x has a slope of 1. So if I drew a line, let's make it dashed. And how about purple? So here is y equals x. There's the line y equals x. So I'm going to reflect this blue function across it. That's a little bit messy, by the way. This is going to continue up like this. Okay, like so. Going through the point 2, 9, 1, 3, 0, 1, -1, 1/3, -2, 1/9. Okay, so there's the graph of the inverse, but they asked us to graph f of x. Well, I was able to graph the inverse because I know how to graph functions that have exponents. Exponential functions are easy to graph. Okay, so what's the next step? Well, step 4 says to plot the points from the table, which I've done, or that was step 3. Connect them with a smooth curve. I've done that. And now step 4, because f of x equals the log base 3 of x, okay, our original, and g of x is 3 to the x, right here. and they're inverse functions, then the graph of f is obtained by reflecting the graph of g in the line y equals x. So I've graphed that. And to do this reverse coordinates, to do this, you reverse the coordinates of point G of the points on G and plot these new points on the graph of F. So what they're basically saying is, now what you're going to do is you are going to call this X and call this F of X. So if I go to 1/9, I get -2. So if I go over 1/9, I'm down at -2. I'll do this one in red. So 1/9 -2 is here. I'm just switching the x's and the y's because that's what you do with inverses. So this would be the point 1/3 comma -1. So go over 1/3 and down 1, which is about here. And then over 0 up 1. So I'm sorry, over 1 up 0, going backwards, over 1 up 0. So it's crossing at the point 0, 1. And then we're going to go over to 3 up 1. So go over 3 up 1 is right here. And then finally over 9, which is here, up to 2 is here. And this is going to continue down to infinity. And this is going to turn and curve and go just like this. Okay, so that is a reflection. Actually, it's going to get a little bit larger. That there, it's not going to flatten out. It's going to grow to infinity. So let me just try to fix this. It's just hard to draw with my pen. Okay, so like so, and I had the 0.92 right there. And so there is f of x equals log base 3 of x. And g of x equals 3 to the x. So always label your graph. So there is graphing a function, graphing a logarithmic function. And those are the 4 steps you take. Find the inverse, make a table, graph the inverse, switch the x's and the y's, and graph the original function. Okay, so now you should be able to do problem number 55. Okay, that brings us to the end of chapter 6.3. Hopefully you're comfortable with logs and natural logs, common logs, everything about them, base E. And here are the exercise problems that I asked you to do as we went. So thanks for watching and have a great day.